Everyone, here is our final project presentation. Our project is related with segment analysis model, that gigantic and versatile strum segment model from Meta. And we want to translate this into a object classification and detection model to do the cell blood classification task. The original cell blood classification task is the SOTA one is use tidy YOLO, and to do the comparison, we also use ResNet 50 and MobileNet and VGG to compare with our SAM model. The specification of dataset is shown below. We have 300 training set and 60 for test and validation respectively. And in the right side is our image, and the purple one is the white blood cell. The other light, the slight pupil is like the red blood cell, and that small deep pupil dot is the platelets, which is the third blood cell in our body. Here's our structure of the segment analysis model, and this is just get from Meta. This model is receive image and prompt and use the transform-based structure to encode and embedding the inputs, and then we use the mask decoder to decode the results. So let me first show our final fine-tuned results of our model. The red star is the original center of that cell, and it is very clear, and the green one is a prediction of our model to predict where the center of a cell is. And it is obvious that all the center predicted are all in the same cell with ground truth, and they are very close. The aim of our project is to turn this extremely versatile and strong pre-trained model into a object detection and classification model specified for medical image. And we'll also try to see the SOTA results of cell blood classification results. Because the current segment analysis model is not oriented to the medical image, it behaves really poor on that sort of data sets. Besides, we normally use the like ResNet 50 or some sort of large with huge dataset training model to extract features. But this time we use a segment model, and we want to use the feature from a segmented model. So that's second obstacles and challenges. So the first solution is that we want to fine-tune the segment analysis model. And the dilemma or the obstacle is that from the model we can only get masks, but in the dataset we only have bounding box. So we need to translate mask into bounding box. Well, it is obviously easy to translate mask to bounding boxes, as we can use just some edge or pixel-wise algorithms to get the correct bounding box from segment models. But that is not continuous and is not differentiated, so it will never have the gradient again. And we want to use the bounding box to calculate IOU, and we want to backward the IOU. So this method we need to clone the gradient from mask. And the second way is like the traditional object detection task. We use MLP to do the regressor. So here's our first part is about reproduce the SOTA results. It uses tidy YOLO, and this one I think it spends my teammates like 1 week to perform this task, and it did achieve the same results with SOTA. The results is shown here, and then my second teammates and the third teammates, they want to use the fast RCN approach to try to exceed the results of SOTA, and indeed they make it. And when you use less than 50, the results is not as good as we expected. The accuracy is relatively low and AME is a little bit higher than we expected. But with MobileNet v3, I think this one is already exceed the SOTA results. In the fast RCA with MobileNet v3 as backbone is strong enough, I think, but it consumes much longer training epochs and training times, so it's not very training efficiency. Here's our structure of our segment anything model. As shown in this flowchart, we only train the mask decoder as the image and propon encoder is trained with versatile and very large image datasets. So we only evaluate on that part, and then we first calculate bounding box from mask, and we use IOU and backward this part of losses, and then we use a pre-trained less than 50 as classifier to produce, and we can sum backward the classification loss. And for the mask decoder part from the bounding box, from segmentation to bounding box, we have two methods, and we also have two methods to, like, we can select mask or the feature map from extracted from the mask decoder sent to the classifier, or we can use the original image with the guidance of bounding box, and we do the center crop, and then we send to less than 50. The original SAM is just, yeah, it is versatile, but it's disaster, as performs very, very poor, and you cannot segment correct for the cell. And if you use this as background to do the bounding box, it's disaster. So our phi2 is want to use the bounding box, first translate mask to bounding box, and then we use IOU loss to fine-tune the model. So these two methods, first method is like a very efficiency and lower model size method. We use algorithms to translate bounding box from segment scenes. And the second one is like we use MLP, yeah, a traditional way to predict the bounding box. But this one is less efficiency and much larger model size. Yeah, and here's our fine-tune results. It's obvious that we can clearly find the boundary of this cell. We will not merge other cells, and it's very accurate and correct compared with the unfine-tuned results. Then we perform our classification task, and so as I mentioned before, it's just like two methods. We use image or use feature map to the classifier. As a result, indeed, the mask input is better, achieves better results in all three, I think, like results. And I think this one is like a lower version of our model, and currently we achieve a much better results compared with the fast RCM backbone mobile 3 v3. But compared with the training efficiency, use feature mask will consume much more time. I think it's like 1.5 times of the time when we just use the image to train this classifier. In conclusion, the SAM is a very strong segment model and can be fine-tuned to well suit medical images and object classification results. But yeah, we still need a more like sophisticated strategy to train our classifier in order to achieve a better accuracy while maintain a comparable efficiency. Even though now our SAM model is much more efficient compared with not only tiny YOLO or the fast RCN. I think that will be our future improvement. Well, thanks anyone. Here's all of our presentation.